Have you ever thought about digging a hole to China? It seems like a logical way to get there instead of flying all the way around the globe. While this sounds like a great idea, it would take you much longer to dig through the Earth than to travel around it. Even if you could dig down that far, you would have a difficult time getting through all of the stuff that lies underneath the surface of the planet. So, if we can't dig that far, how do we know what makes up the interior of the Earth? Well, scientists are able to understand Earth's interior by studying seismic waves. These are waves of energy that travel through Earth, and they move similarly to other types of waves like sound waves, light waves, and water waves. Seismic waves are sent through the Earth during earthquakes, and those energy waves are what cause the ground to shake as they travel through it. Seismic waves are recorded by a machine called a seismograph, which tells us about the strength and speed of the seismic waves. These recordings made by a seismograph are called seismograms. Seismic waves travel at different speeds when they pass through different types of material, so by studying seismograms, scientists can learn a lot about Earth's internal structure. Let's first review the two types of seismic waves, which we learned about in another lesson. Body waves are seismic waves that travel through Earth's interior or its body. Surface waves are seismic waves that travel through Earth's surface. Makes sense, right? Surface waves are important, but they don't provide much information about what happens below the surface. For this, we need to study body waves so that we can see what Earth's body is like. There are two types of body waves called P waves and S waves. P stands for primary waves because these waves travel the fastest and are detected first. S stands for secondary wave because these are slower than P waves, arriving second on the seismogram. Since the information recorded on a seismogram tells us how fast body waves are moving when they travel through Earth, we can tell what type of material they're traveling through. As body waves travel through the Earth's internal layers, their speed changes, causing the wave to bend. This bending is similar to looking at a straw in a half-full glass of water. If you look at the straw from the side, it appears to bend where it hits the surface of the water. This is because the light waves are bending and slowing down as they hit the different material, in this case, the water. The same thing happens to body waves when they travel through the Earth. We know that the surface of the Earth is solid because we can easily see this. But we need body waves to tell us what lies below. What they tell us is that directly below the crust is a layer of rock with a different density. As we learned in another lesson, this layer is called the mantle, and we know that it's a different density than the crust because seismic waves bend and suddenly pick up speed where these two layers meet. P waves can travel through both liquid and solid material, but S waves can only travel through solids. Since both P waves and S waves travel through the mantle, this means that it must be a layer of solid material. The really interesting part about this solid layer is that even though it is rock, it flows like a very thick liquid. It's similar to the consistency of silly putty, which if you punch hard feels like a solid, but if you stretch slowly, moves like a liquid. Another pretty significant change occurs at about 1900 miles down. S waves suddenly stop as if they have hit a brick wall, and P waves bend and slow down so much that no waves are detected at the surface of Earth. What this tells us is that there is another distinct change in density and composition here. And in fact, this is the place where the mantle and the outer core meet. The mantle is made of mostly that liquid rock that moves like silly putty, but the outer core is an area of mostly liquid iron, which is much denser than the rock in the mantle. Since S waves can't travel through liquid, this is why they run into a wall and stop. P waves can travel through it, but they do so much more slowly than through solid material. As P waves continue through the outer core, they suddenly bend again and pick up speed at a little over 3,000 miles into Earth's interior. This is where the outer core meets the inner core, and we know that it's solid because the P waves pick up speed yet again. While studying seismic waves from earthquakes provided scientists with a lot of information about Earth's interior, much of what we know actually came from nuclear weapons testing during the Cold War. During the 1960s, both the U.S. and Soviet Union tested nuclear weapons by exploding them underground. These underground explosions produced seismic waves similar to the ones produced by earthquakes. Both countries used very sensitive seismographic stations to monitor the testing activity of their opponent, and without intending to do so, produced seismograms that provided detailed information about Earth's mysterious interior. Just because we can't dig our way down into Earth to see what it's made of doesn't mean we can't learn about it in other ways. Seismograms, which are recordings produced by seismographs, are the main way that scientists know what Earth's interior is made of. We can see that the crust is solid material, but we require body waves to tell us about the rest of it. We know that the mantle is solid because both P and S waves travel through it. We also know it's at different densities in the crust because both types of body waves pick up speed as they hit this layer. We also know that the outer core is liquid because S waves hit this layer of Earth like they would hit a brick wall. They can't travel through liquid, so this is where their journey ends. P waves can travel through liquid, but much more slowly than through a solid. When P waves hit the outer core, they slow considerably, telling us that they've reached a much denser material than in the mantle. Another significant change in wave speed occurs at the edge of the inner core. Here, P waves bend and pick up speed, telling us that the inner core must be solid material because P waves travel faster through solid than liquid.